All right, here we go. Hit the present button. All right, hello, Professor Price, and whoever else is watching this. My name is Thaddeus. I'm going to be presenting on the artificial artery simulation. And just kind of walking through how I did it and why I chose the material I did and my recommendations for choosing that material. So let's get started. So some historical background real quick. Basically, there was two methods historically that were developed. The first method was growing these arteries in scaffolds. Historically, that was pretty difficult, but it's becoming pretty easier with the development of 3D printing and additive material development. So that's looking promising. And the other way was artificial material development with polymers. The main three materials that were used that I found were expanded polytetrafluoroethylene. I think that's right. And then per is polyethylene or polyurethane, and then polyethylene tetraphthalate. Sorry, I'm not a chemist, so don't know how to pronounce those. But those are the main three. So those three kind of broken down here in this table right here. So for EPTFE, that's the most expensive one, significantly more expensive than the other ones. It's not non-biologic, obviously, because it's synthetic. It's got high strength, it's comfortable, and its users, it doesn't kink, which is very important when considering blood clots and stuff. And it's re-sterilizable. I'm not totally sure why that's beneficial because, well, if you have extra material, I guess there's less waste, so that's good to consider. PUR, significantly less expensive than the other ones, still in the middle range of expense. It's strong, elastic, transparent, and it resists infection, which is super important when it comes to implants because infection is actually the single most common reason for implant failure. So you want to make sure you're avoiding that. PET, by far the cheapest. Tissue ingrowth means that it actually interacts with the body. It's biocompatible, which also refers to it interacting with the body. Those are both very important things when it comes to implants. High patency and homeostasis, all those things just basically mean that it interacts with the body well. So that one's looking pretty promising in terms of cost and how it interacts. Notice it's not very strong, so that's what these next simulations will kind of evaluate. These are the material properties for each of those. So kind of compared to a human femoral artery, this was just found based on some data gathered, but the Young's modulus of the femoral artery significantly lower than the materials gathered. Everything's basically lower. So Poisson's ratio is lower, shear modulus is lower, mass density lower, all of it's lower. So what that means is that the synthetic materials are just going to be stronger, more elastic, and potentially could work a little better, but there's also a few things you need to consider, like stress shielding, all that kind of stuff. So not super important though for arteries because they're not actually like structural things. So you're mostly just looking at making sure that it will actually hold up to certain pressures and shear rates. So next thing, so to simulate this, the goals of the simulation is to evaluate the materials. We're going to evaluate the cost, as we just discussed, the mechanical properties, the physical properties, and then the shear stress that's caused by blood flow. So the simulations will pump blood as the fluid through like a model of each of these arteries and kind of see how the shear stress is acting on the walls of that artery. Methods continued. So this is the model dimensions. This is just one drawing. It was simulated at 10 millimeters, 100 millimeters, and 1000 millimeters. But it was found that the femoral artery has a wall thickness of 1 millimeter and a rough diameter of 10 millimeters. That's on average for males in the range of, I think, like 30 to 50. So that's just an average there. And like I said, the lengths that are being simulated are 10, 100, and 1000 millimeters. And yeah, these are just the rough dimensions of that. Like I said, the length changes depending on what model we're looking at. But each of the three materials that were listed are going to be evaluated under these conditions, resulting in a total of 9 simulations. So a little bit into the flow simulation variables. So the average cardiac output of a male while exercising is 25 liters per minute. So that's going to be used as our flow rate. The blood viscosity on average is 4.5. What is it? Centipicos, I think. CP. I forget what that is, but CP. Density 1,000 kilograms per meter cubed. That's just density of blood. And then it's gonna the output. Oh, so the input boundary is that on the next page? Hold on. Yeah, boundary conditions. Okay, cool. So the flow simulation boundary conditions. The inlet volume flow rate is going to be 25 liters per minute, like I just said. That's going to be coming in at 310.15 Kelvin. And the outlet pressure is going to be 16,500 pascals, which is the maximum pressure that the heart is pumping against. So I think I had set it, like if we go back to this one, the outlet is where these arrows are going towards, and inlet was back there where the coordinate system is. So yeah. And then the mesh I set to 7, just so we had a nice fine mesh. And then the computational domain was just fit to the model. So yeah, and then this is just showing one of the results. So it kind of has, as you can see here, most of the shear stress, actually this is a pressure plot. Most of the pressure on the wall, the inner wall of the artery, is up at the front, and it decreases as it goes through the artery towards the end. That's why it's blue over there. And then the maximum is about, let's see, it's like 3,500 more, about like 3,000 more pascals than the input. So, you know, it amplifies a little bit, but not too much. This was the results of it. As you can see, the results did not change depending on the material. Likely an error with that could have been how the boundary conditions were set up, or how the inlet conditions of the model were set up. I couldn't quite figure out what had happened with that, but as you can also see, the length increases. The more length, the more shear stress the model experiences. This is the maximum shear stress, by the way. So yeah, so it looks like length of the artery is actually more impactful than the material that's being used in terms of the flow simulation. So based on that, relatively the same results for each model, for each material. Length increases, like I just said. Incorrect boundary conditions, incorrect fluid conditions, or rerun issues. I was running it on the same setup, so it could have just been like rerunning the same thing. And I might have been a little bit better off to set it up each time. I'm not sure if that has an effect, but that's just something I was thinking of. So so just an evaluation of the materials, EPTFE, that ends up being way too expensive. It's significantly more expensive than the other ones. Doesn't offer any advantages in terms of the simulations that were ran. So we're gonna toss that one aside. PUR, it's somewhat expensive, but it is resistant to infection. So depending on how prominent infections are, that might be a good option. PET just ends up being the cheapest, and it's biocompatible. So likely that's the best option. Biocompatibility is super important, but again, it's not very strong in comparison to PUR. So PUR might be a good option also. I think in my final consensus was that PET was the best option, just because it was cheapest, biocompatible, which means it's likely resistant to infection. It didn't show any difference necessarily in comparison to the other 3 models. So yeah, so that's it. And there's my sources. So thank you all for listening. Appreciate you all, and enjoy the rest of your day.